I'm going to talk about switch capacitor power amplifiers. First, I'm going to motivate why I think it's an interesting topic. We'll look at a couple of different topologies of switch capacitor power amplifier and some potential future research directions and conclude. So ultimately, the motivation in going towards digital power amplifiers is that we have this new topic called software-defined radio. And software-defined radio is a beautiful thing if you have analog hardware at the front end of a radio that is widely tunable as well. So software-defined radio, we define the radio signal purely in software. We reconfigure a digital signal processor, and we have to ultimately pipe it to some analog front end. And so the way we do that is we take our baseband and we upconvert the baseband signal to an RF frequency, and we input it to the power amplifier, and the power amplifier interfaces with the rest of the world. Now, I'm not talking about the receiver here because largely a lot of the receiver challenges have been solved. The transmitter has a particular problem, mainly a problem with the RF power amplifier. And why is that? Well, to make a power amplifier, we need to put out something like on the order of 1 watt for a typical wireless communication signal. It's going to be cellular or a little bit lower for Wi-Fi or Bluetooth. Nonetheless, somewhere on the order of 1 watt, and we need to have an average efficiency for that power amplifier of above 25% if possible. So if we use a linear power amplifier, we have what we would call modulation reconfigurability, because whatever input signal we put into the power amplifier, we get a linear replica out of the power amplifier that's just larger. If we use a digital power amplifier, we'll see today how we make it a digital power amplifier reconfigurable, at least in terms of the input amplitude. But the thing we get out of the digital power amplifier is that it's much more efficient than a linear power amplifier. To make it a true software-defined radio, we need to make this power amplifier not just tunable in terms of the linear interface, in terms of linearity with respect to input amplitude, but we also need to make it broadband in terms of the frequency response. And so there are a number of different ways to do that, and the way that most software-defined radios do that nowadays is they have parallel RF front ends. So we take several different front ends for small bandwidths, and we parallelize them, put them together. And that's fine if you're doing this for a base station. If you have some kind of, if you have a large box that you can put this into, that's great. And right now there are lots of research opportunities for this. So there are Edis Research, National Instruments, software-defined radios that you can buy. And it's in a box that's about 5 or 6 inches on the side, 2 or 3 inches tall. If you want to ultimately integrate these things into something that you can carry around with you, your cell phone, smartphone, that doesn't work too well. The other thing we can try is make really wideband RF front ends, but this is a problem because we need the matching, we need the PA to provide some filtering, because the power amplifier is going to be fairly nonlinear, so we want to be able to avoid any kind of harmonic distortion, so that we don't cause or create interference. So the way that I like to look at it is that we need to go towards tunable RF front ends because this will be more integration friendly, but currently it's very lost. Now, we're only going to address really the programmability, at least with this research, programmability with respect to integration. But I'll show some ways that we can start looking towards it as well. So this is why we work on power amplifiers. It mainly has to do with energy efficiency. So when it comes down to it, the RF power amplifier is a dominant single block energy consumer in a radio. And as we have it around here, it's a bad piggy. It consumes more energy than it really has to. This is going to be a growing problem. On a smartphone, we have typically 3 to 6 power amplifiers. So we have power amplifiers for multiple bands of cellular, 3G radio, 4G radio, Wi-Fi, Bluetooth. So it's getting to be worse and worse problem. And really, this is an illustration of why it's a problem. So if I look at a typical linear power amplifier, and I have a Class B power amplifier here. Its peak efficiency is 78%, but the efficiency characteristic rolls off as a square of the envelope voltage. So whatever our modulation envelope is, our efficiency rolls off as a square of that. Now, if we look at a modern OFDM communication signal, orthogonal frequency division, multiple access, it has a probability density function with respect to its envelope that is rarely distributed, has a peak to average of something like 13 dB. So the average value of the signal is around here. If we look at the efficiency at the average value of the signal, we see that the linear power amplifier has an efficiency somewhere in the range of 4 to 5%. So we'd expect our average efficiency to be no better than 4 or 5% with that kind of PDF. And that's very problematic. So what we're going to try and do is raise the efficiency of the amplifier and also shape its efficiency characteristics where it better fits the probability density function that we expect to see with the types of communication signals we're looking at. One comment, why on efficiency, another comment on efficiency. So that was just efficiency with respect to input voltage, but we also have the efficiency with respect to the impedance transformations. And impedance transformation is something that we do in order to try and get a lot of power out of a power amplifier. So a typical antenna impedance is 50 ohms. And if you look at a modern CMOS process, the supply voltage is somewhere around 1 volt. So we can look at our output power as something on the order of the supply voltage squared divided by 2 times the impedance. So if we were looking at 1 volt and just using 50 ohm antenna, we'd be able to get something on the order of milliwatts, tens of 100 milliwatts. Now we mentioned earlier that we want something on the order of a watt out for our power amplifier, so that's already no good. So we do something called an impedance transformation to lower the impedance of the antenna down to a lower impedance that will get us more power output. Now, the problem with this is that the efficiency of the matching network that we use, the bandpass matching network, is raised with increased impedance transformation ratios. So as we try and take our antenna impedance, which is 50 ohms, down to some lower impedance, the quality factor of the network is increasing. And we have an efficiency of our matching network that's related to the quality factor of the inductor, how much losses in the inductor divided by the quality factor of the network plus the loss in the inductor. See, if we increase this quality factor too much, the efficiency of the matching network rolls off, and that's exactly what we see here. What this does is it limits our network quality factor to something along the lines of 1/5 to 1/6 of the quality factor of the inductor itself. So we're just looking at how much loss is in the inductor by itself. And this means that our matching network would have an efficiency greater than 75 to 80%, some of that ballpark, depending upon what the peak value of the inductor quality factor is. So this is one reason why it's fairly difficult to make very efficient power amplifiers. Okay, so let's look at what we can do to fix the efficiency. And what we're going to mainly look at here is how do we raise that peak efficiency from an ideal peak efficiency of 78% for a linear power amplifier up to 100% for a switching amplifier. So the first thing we have to look at is what causes the efficiency degradation. And if we look here, we have linear power amplifiers going from class A to class C. So class A, we bias the device so that for any input swing, the device is always on, it's always conducting current. So it has some quiescent current that's flowing through it at the same time that it has a supply voltage across it, and that means that the device is dissipating power. And that's bad for us. Now what they did with the class B amplifier to fix that is they bias the class B so that it only conducts for half the cycle. So when the voltage swing goes above the threshold voltage, the device conducts current. When the voltage swing goes below the threshold voltage, the device is cut off. We only conduct current for half of our cycle, and this gives us an energy efficiency. We can look at a comparison between a class A amplifier and a class B power amplifier, and we see basically that the peak efficiency would be when the output voltage is equal to the supply voltage. And for a class A, the peak efficiency would be 50%. This isn't very good. This means that for every 1 watt we're generating, we're dumping 1 watt into heating up the environmental environment power amplifier. That's not very good. Class B power amplifier, we see that we have an efficiency, a peak efficiency of pi over 4, which is about 78%. So we do a little bit better, but again, it rolls off as a square of the output voltage. It's not very good. We have a couple of other linear amplifiers. These are only linear because for some part of the cycle, the output current is dependent, is a function of the input voltage. It doesn't necessarily mean that they're linear with respect to. It doesn't mean that the input voltage is a replica of the output voltage, or I should say that vice versa. We have a class AB, which we bias somewhere between class A and class B here, and we also have a class C amplifier. I'll talk about class C a little bit later. The interesting thing about class C is as we lower the device's bias voltage, the efficiency tends towards 100%, and unfortunately it does so right when the device completely enters cutoff, so the power out that you can get is 0. But if you need a small amount of output power, you can get very good efficiency, and so we're looking at this for body area noise. So the thing that we notice about CMOS is that CMOS devices have been optimized to be good switches. So we use CMOS devices for microprocessors, so all the optimization for performance has been to make the device a fast switch, not to make it a very linear transconductor. So one thing to ask is if we're going to try and make power amplifiers in CMOS, why use them as linear transconductors? They're not optimized for that. We can use them as switching amplifiers. Now we have a couple different classes of switching amplifier, D, E, and F. We'll be mainly looking at this class D amplifier. But what all switching amplifiers try and do is make it to where the voltage at the drain is never non-zero when the current flowing through the transistor is non-zero. We have voltage and current are non-overlapping. And what this means ideally is that we get a lot of power out from this thing, but the transistor itself doesn't dissipate very much power at all, ideally 0. And this means that our efficiency is 100%. The problem with a switching power amplifier is that it has no sensitivity with respect to input amplitude. We put a signal in that is designed just to cross the threshold voltage of the transistor to turn the device on, and then quickly turn the device off. So we have to do some other things in order to linearize the amplifier, in order to make the output linearly proportional to the input. This is what we would call a digitally modulated power amplifier, and there are a couple different versions of this. In this version by Capacitor from ISSCC in 2007, they made a digitally modulated supply modulator. Basically, this DAC input a code into the supply modulator that was composed of many different parallel current sources, and you could turn on or turn off parallel current sources as desired. A separate version of this from Kresge just made the supply modulator as a decoder. So essentially what happens is an amplitude encoder comes in and can turn on any in-unit PA cells. These are current-based cells as well. So basically, as we turn on or off these cells, we can change the amount of current that flows into the output resistance and generates a voltage. So basically what we've done here is combine a digital to analog converter with a supply modulator, but we've done it in the digital domain with this decoder. So it's tiny. You can make digital circuits very small. Now I just mentioned that these two versions we're using some kind of current cell-based approach, and what we're going to be talking about mainly is the capacitor-based approach. But why do we want to talk about a capacitor-based approach? So if we look at this current-based approach, we have individual current cells, and we have a code word that can selectively enable or disable these switches. So we can either be putting a lot of current through if all the switches are turned on at the same time, or only one of these switches is turned on at the same time. We can put a very small amount of current through. And the problem with that is that when we start putting a lot of current through, we get a fairly big voltage drop across the current source. And we want to keep the current sources saturated, so we want to keep a large voltage across the current sources. What ends up happening is that as we increase the input code, we have a lot of current going through here, we get a lot of voltage drop. The output characteristic becomes saturated with respect to the input code. And what this means is that if we wanted to have a good resolution in terms of number of bits that we see at the output, we would need to do something to compensate for this, which would be a pre-distortion technique. So we have to have a few extra bits for pre-distortion. The other thing we could try and do is do an analog fix. We could make cascaded current sources, but the cascaded current sources themselves require more voltage headroom, and that would cause us to burn more power. So we get lower efficiency. The one nice thing about this architecture is that we do get better efficiency. The efficiency is proportional to the square root of the voltage rather than the square root of the voltage. So this should beat a linear power amplifier right off the bat just from math. So now let's look at the switch capacitor amplifier. So we'll start with a few basics about switch capacitor. So the switch capacitor circuit, there are two different types. We have a pre-charge and reset, and we have charge redistribution without recharge. So in this case, we're going to switch the voltage from the supply voltage onto a capacitor. So we're going to charge this capacitor up to a charge VDD times capacitance. The energy stored in the capacitor would be 1/2 CVDD squared. Now, in the second cycle, we're going to open that switch with respect to VDD, and we're going to close the switch to another capacitor. And now that voltage the charge will have to redistribute across the array, and we would get the final energy state of basically the initial energy state over 2. So we've lost half of our energy in doing this charge redistribution via pre-charge and reset. We could notice that if we just sample on the bottom plate of one capacitor and let it redistribute across the array, the energy in this state versus the energy in this state is the same, so we don't lose any energy. And what's important to note here is that we got some amplitude control. We started with a voltage of VDD, and we ended up with an output voltage of VDD over 2. So this is the mechanism we're going to use in order to get some amplitude control visually. Same thing in this case. Started with a voltage where we switched between ground and VDD, ended with an output voltage on the top plate of the capacitor that's VDD over 2. That's pretty good. Got amplitude control. Now we just need to figure out how to harness it. So what we know in a CMOS processor with it, or any integrated circuit process really is that capacitors are fairly easy to array. So we can design a capacitor such that we share a top plate. So have a big metal plate on the top, and we divide bottom plates on the bottom and connect to those. And we can either switch all of the bottom plates, or we can hold some of the bottom plates to those capacitances to ground. So if we switch all of the bottom plate capacitances, we would get the voltage of the output should just be the voltage of the output should just be going between VDD and ground. We can't change the voltage across the capacitor instantaneously. So if we switch these capacitors between ground and VDD, then VDD should instantly show up at the top plate. Now, the charge redistribution trick comes in if we say only switch some of these capacitors, and we hold some of these capacitors at ground, then effectively we have kind of a series capacitance. And so the charge will redistribute across the array. So if we only switch half the capacitors in the array and hold the other half at a fixed potential, then the charge redistribution would be when it would cause half the voltage to show the output. If we switched a quarter of the capacitors and held 3/4 of the capacitors at a fixed potential, we would see 1/4 of the output voltage. So this is basically if we make a bunch more of these capacitors. Here I've shown 4 capacitors, but if we make a bunch more of these capacitors, then we can get a lot of resolution from our digital analog converter. And that's basically what we're doing. We have an RF switch capacitor, RF to digital, and an digital analog converter. Now let's look at output power with this system. So we can look at our switching voltage sources being little n over n times the supply voltage. This is little n is the number of capacitors we're switching, big N is the total number of capacitors in the array. Supply voltage is just whatever supply voltage we have in the process. So we're going to switch our capacitor array with this code and look at the output power. And what we want to see is that we get some kind of linear output power, output voltage with respect to our input number of capacitors being switched. And that's exactly what we see. We get 1/2 times 4 over 5 times n over n times the supply voltage. So as we change n linearly, we get a linear output voltage. Now, power is just our voltage squared 2 times the resistance. So we'd also expect to see some linear variation in output power. A square variation in output power. Now, a couple things that we'll note a little bit later on is that the linearity of the system is going to be determined by matching rather than keeping transistors saturated. And we'll also find that it's going to have to do with, our linearity is going to have to do with parasitics, and we'll look at that in a bit. Now, we also have some dynamic power dissipation in the system. So we have to turn on, we have to switch on and off capacitors, switching on on and off capacitors means that we have to charge them through some resistance, and that means that we're going to burn some energy. So how much energy do we burn ideally in the system? Well, we have the charge and discharge capacitance each cycle, so we get what we call the capacitance times voltage squared times frequency dependence energy. So that's our dynamic power dissipation. So what we're going to do though is assume that I can turn this switch on and off very fast. That's a very fast rise and fall time. And what that means is that the inductor here doesn't allow current to change very quickly. So I can treat the inductor like a current source if I'm turning on and off the switch very quickly. So I can make an equivalent circuit for power estimation that has the inductor just being an open circuit. So now my total capacitance in here is just a series combination of the capacitors that are being switched to the capacitors that aren't being switched. And I can see that my power dissipation then would be this n times n minus n over n squared c v squared times f. Yes. These are being switched at the RF frequency, at the RF carrier frequency. So for the one with C, 2 gigahertz. The code, the amplitude code is changing much slower than that when we're switching these at the RF frequency. So we'll look at the entire circuit. Okay. One important thing to note here is that this actually peaks for some middle code word. If n is equal, if little n is equal to big N, then the power dissipation goes to 0. If little n is equal to 0, the power dissipation goes to 0. So this peaks somewhere in the middle. That's important. Basically, what that means is that the ideal efficiency, because the power dissipation is going to go to 0 at the peak, goes to 100%. So we can look at power added efficiency for this system, and we define power added efficiency as just being output power divided by our output power plus that power being dissipated in the capacitors. And we're going to see that it's going to be dependent upon that loaded quality factor of the PA. That was the Q network from the first or second slide. So we know that our typical inductor quality factor is going to be in the range of 20, and we want to use maybe a factor of 5 lower loaded quality factor for the network. So it means that our loaded quality factor is limited to 3, 4, 5, somewhere in that ballpark. This tells us that now, since we know what size resistance we need in order to get the desired output power out, we can size our capacitor in our array. The important thing to note here is that if we look at a conventional digital power amplifier, its efficiency characteristic is this magenta color here. We already know that that power amplifier had an efficiency characteristic that was better than a linear power amplifier. Now, so what we want to do is be better than that. If we're better than that, everything's good. So even for a loaded quality factor of 1, the switch capacitor power amplifier has a higher efficiency. Now we expect to get a loaded quality factor of 3, 4, or 5, somewhere in that range. And we see a significant improvement in power added efficiency for this that case. That's what we're looking for. Now we also have some practical things that we didn't consider in that. That was an ideal efficiency calculation. That would give us an efficiency of 100% at peak. We know that we never see any system in the universe that gives us 100% efficiency. So where else do we get hit? We get hit in a couple of places. So if we have to write practical efficiency calculation, we would include these factors alpha and beta, and these are just loss factors from the fact that the inductor that we use itself has some loss in it. The parasitic resistance, the CMOS switch does not have 0 on resistance, it has some parasitic resistance. And then also we have other parasitic capacitances that we have to charge and discharge every cycle. So we have switching parasitic capacitance. We have switching drivers that all have capacitance that has to be charged and discharged every cycle. And we also have a clock distribution network. So we add these in here. And these are all going to be dependent upon some number of cells being switched times the capacitance of that cell times VDD squared times F. What's important to note here is that unlike most power amplifiers, we see an efficiency degradation as we scale. These things, our parasitic capacitance here should get smaller with scaling. So as we scale process nodes, we see smaller capacitance. That means we dissipate less power dynamically. If we look at a practical calculation, we see that our peak efficiency, this is a practical calculation for a loaded quality factor of 3. Practical efficiency is going to peak around 45%. We expect it to go up with scale and process generation. Now, if we compare that to what we could do in the same process with a linear power amplifier, it's the peak efficiency here is still probably 5 to 10% better than what we can do with a linear power amplifier, and rolls off more slowly than a linear power amplifier. So it's definitely better. Now, one of the problems that we have is what we're effectively doing is using a CMOS switch as a voltage source. And so this is kind of problematic. So we have this ideal representation shown here where we're switching between ground and VDD, and we have an ideal switch there. In reality, we have a CMOS switch. So we use a PMOS transistor to switch between VDD and the output, and an NMOS to switch between ground and the output. And those capacitances have, if those transistors have some parasitic capacitance, that parasitic capacitance isn't necessarily well matched. The PMOS is going to have a different parasitic capacitance than the NMOS. And the other thing is the on resistances are probably not very well matched either. So we need to do things to make those well matched. So slicing the transistors well, using dummy transistors, layout techniques. Why is it important? Well, we look at a couple of different situations. So here we have a situation where we're trying to output a very small voltage. So we're only switching one capacitor, we're holding the other 3 capacitors close to the ground. So we see quite a bit different parasitic capacitance and parasitic resistance in this case than we see in this case. Here we have 3 transistors effectively in parallel, here we have 1. If we go to another code where we're trying to output a higher voltage, we have 3 transistors we're switching, 1 that we're holding at a fixed potential. So we see it basically a mismatch in parasitics. And what that shows up as is what we, in PA parlance, power amplifier parlance, call amplitude phase distortion, and amplitude modulation, phase modulation distortion. So we see here is as we change the code, the loading from the switches changes. So we see a delay that's code dependent. And we also see some amplitude variation as well. And that amplitude variation is called AM to AM dependent. They're amplitude modulation to amplitude modulation dependence. Now, another thing to note here is that faster switching, smaller transistors will improve this performance. And we've actually taped out a generation of this, 2 generations of CMOS and seen an improvement. Also, we learned some lessons about layout of these types of systems. So it's hard to tell exactly how much it was due to, how much the improvement was due to our knowledge, and how much it was due to the process. But nonetheless, we'll see some results that show improvement. Okay, so this is the whole schematic. And we laid this out, we designed this so that we have bit slices. So each of these bit slices is just our, we have a cascaded switch that is guarding the bottom plate of the capacitor, and the top plates of the capacitors are all combined. And we lay these out so that when so they're pitch match, so that we can basically just copy one cell. So if we designed one cell, we can copy it n number of times, where it might be the number of bits we're looking for. In this case, we have a 6-bit system. So we've done a trade-off here. We have a binary thermometer decoder. Binary thermometer decoder just takes a binary code word and trains it so that the binary code word increases linearly. So as we increase the code word, the number of capacitors being switched increases linearly. The problem with that is that that gets really big really fast. So that's going to grow as the number of bits squared. Whereas the binary array grows smaller. Now we made a trade-off here between trying to keep the array small, so we keep some bits in this binary thermometer decoder and some binary bits. The binary bits are going to be less accurate. It's harder for us to match these capacitors. These ones we can match fairly well because they're all the same size. We expect to see fairly good uniformity in the CMOS process. But here we're doing some scaling, and so it's harder for us to match the capacitances exactly, and also the parasitics of those capacitances in the chain. Now, this is the matching network. So we use what we call a tap conductor matching network. The output, this is a downward impedance transformation. So we have a 50 ohm impedance here, the output, and we have to transform to 3 or 4 ohms. Basically, we just have a DAC that's driving a really low impedance. power up. Okay, so results we'll go through fairly quickly, but we see our here we're changing the digital code word, and we see that our output power is changing with that code word. It's hard to see that, whether this is linear or not. We'll look at voltage with respect to the input code and to see that linear. But the important thing to note is that is efficiency. So we get a peak efficiency of about 45%, peak output power around 24 dBm. That's about a quarter of a watt. Not quite what we need for cellular, but we're getting there, and if we use some power combination, we can get the rest of the way. And more important, our efficiency rolls off less slowly than the linear power amplifier does. So we'd expect the average efficiency across the modulation envelope to be better. One other thing to note is that if we did this with a 6-bit implementation, but if we wanted it to be bigger, if we wanted more resolution, it wouldn't be too hard. The capacitor array is right here, and if you compare that to the matching network, the two inductors, and all the driving circuits, decoder, decoder, bypass capacitance, etc., the capacitor array is actually quite small. You get double the size of that array without really affecting the area of the circuit. Now, what's important, so we'll look at linearity. We see a weak second order nonlinearity across the entire code range. That is mainly due to the parasitic mismatches that we saw earlier. But what this ultimately translates to, fairly significant AM to PM distortion. We fixed that a lot. What this translates to is this is what we call a spectral map. So the FCC tells us what kind of window we have to transmit our energy in. And we're supposed to, the gray curve basically should stay below this black curve for all power. So you can see here we didn't. But we're fairly close, and most of the reason that we're not below this has to do with the fact that we sampled at a fairly, we changed the envelope code word at a fairly low rate, which means that these aliases were not getting frequency shaped as much by the matching network. And we'll fix this on a subsequent version. I'll show you those results. But the nice thing is we got an average power output of 17, almost 18 dBm with that 13 dB peak average ratio, and an error vector magnitude measurement of 2.9%. And this is just a measurement of how well we're hitting our target constellation points. Just for point of reference, the specification, this is a Wi-Fi signal, the specification is 5.6%. So don't quite meet our FCC mandate, which is probably more important than meet because the FCC will come and arrest us or fine us if we're selling this. But it does, the linearity is enough to meet the EVM, so we would be able to demodulate it very well. We'll look at the Class G version of this. So what does Class G mean? Well, it means that we're going to smartly switch between two different supply voltages.
Maybe cover this one. The results that you're showing physical devices that you did for your simulation.
No, they're physical devices. Yeah. And, this is the actual chip we take down. And we take down a couple of different versions of this.
Is there like a big difference between the physical device and the simulation?
Not if we modeled it very well. So what we did was went back and modeled the losses in the switch. So we try and do some kind of behavioral modeling to match the device. So there's a significant difference at first, and then we iterate with it. Okay, so going forward, what we did is, well, why do we use a big supply voltage when the input code is relatively small? And so that's the question we asked and answer here. So what we could do is use a voltage that's twice some other voltage, and when the envelope is big, we operate from that big supply voltage, and when the envelope voltage is small, we switch down and operate from a lower supply voltage, and this will save a lot of power. So basically what we've done is we've taken this original switch capacitor array, and we've added another switch to each of these capacitors. So they switch between supply voltage and ground, or between twice the supply voltage and ground. This gives us improvement efficiency. We'll see why. So if we look at our original efficiency characteristic, this was our output, normalized output power, and this is the normalized power being consumed by the switch capacitor array. We said that that would be minimal as a code of 0 and as a code of at a full code, and it would So here, if we look at our efficiency, we'd expect our efficiency to peak at 100% and then roll off down towards 0%. And somewhere in the middle, we're consuming the most power in that series. So if we could do something to drop this power down in the middle, we'd improve our average efficiency. Now that's what this using a second supply voltage does. So if we just use a traditional class G network, we have the same output power characteristic, and we see that for large codes, for normalized output voltages above 1/2, we see that same characteristic. And then at this point, we would switch to using a smaller supply voltage, and we'd see our power dissipation would be a lot smaller. So if we just use a class G topology, our efficiency for voltages above 1/2 volt is the same as it was before. And then by switching to that smaller supply voltage, we get high efficiency at low output voltage as well, which is good. We're shaping that efficiency characteristic more towards what the probability density function of the modulation schemes that we're looking at. Now, what we note is that we actually have a digital platform here. We can program this thing to do whatever we want. It's just a code word. So this is done in signal processing. If I change the way that I code this system, I can make my efficiency characteristic do something like this for both schemes, just by changing the way I program my amplifier. And so what we see here is that actually, if we change the coding, we can get a better efficiency characteristic for voltages above that half normalized output voltage, and for voltages below that normalized output voltage. And the way we do that is just by smartly changing how we do the coding. So what we see here, this is a 3-bit array with 4 bits of resolution. We get 1 bit of resolution by using 2 supply voltages that are binary weighted in the node. So what we see here is binary thermometer coder. So as we increase the binary code word, we get a linear increase in the number of capacitors that are being switched to VDD, between VDD and ground. So then when we get above a certain point, we start, instead of using the single supply voltage, we use twice the supply voltage and linearly ramp that up as well. This gives us a linear code, and it gives us that traditional class G. But what we can note is that if we can improve the switch, and we'll look at that in a moment, if we can improve the switch topology, we can linearly ramp up the supply voltage until it reaches the single supply voltage until it reaches a max code. And then we can start using both the single supply voltage and twice the supply voltage and linearly ramp that up as well. And if we do that, we get that improved efficiency characteristic. So this is just coding, nothing else. Looking at what our efficiency characteristic looks like, so we have our efficiency of the original switch capacitor array, the red curve here. If we use the traditional class G approach, just using 2 supplies independently, we get this characteristic blue curve, and that improved coding gives us the magenta curve. This is really an interesting result. We get very good efficiency compared to a linear power amplifier across the band. Across the expected input voltages. Now, what we have to do to make that happen is we have to take this original switch and we have to add some mechanism in to switch to a lower supply voltage. So this switch was designed to be able to switch to twice VDD. We need to add some way to switch a second supply voltage in that's VDD. And the problem we're going to have here is if we just add, say, a PMOS pass transistor here, and we switch and we try and pass VDD through this transistor when we turn this transistor off, we're going to get a significant amount of leakage current. So a lot of current is going to flow between VDD and this device because we have a large voltage across this transistor. We get leakage current. That's going to affect our efficiency. So what we did was made a voltage tolerant switch where we pass through the switch and depending upon the code word that's coming in, we either have this CMOS device that's going to be turned off and going to minimize the leakage current. So this would be when we're trying to push VDD over to the output. This device helps to keep current from crowbarring through this cap. And when we are trying to get VDD out, we stop switching this one, and instead switch this transistor and move the supply voltage on this one to VDD over 2 to turn on device on, so it has a the nice thing about this is that it's very reliable. We don't stress any of the transistors, and we minimize leakage, so we minimize additional power consumption. Same type of final circuit. This is a 6-bit capacitor array where we get effectively 7 bits of resolution. And the reason we get 7 bits of resolution is we have one supply voltage and twice the supply voltage, so we get a binary reading from that supply voltage switching as well. Now, one thing to note also, and what we're going to look at is we need more resolution. I'll cover that why in a minute, but I did mention that we can make a larger array fairly easily. We're going to run into some other issues as well that need to be worked out. But we can get additional bits. We stopped at 7 because that was what we needed for the modulation input. We went power control. So this is a switch capacitor power amplifier, Class G switch capacitor power amplifier. And notice a couple of things that are different about this. There are no passive devices on this one. We didn't put conductors on this one because we flip chip onto it. So most digital chips nowadays are being, they have these little, what they call bump ons on the bottom. They have pads on the bottom of the chip, and they just flip them over and bond them directly to the PCB or whatever package we're using. And it minimizes lead inductance. So it's minimizing parasitics. But the nice thing is we have a really small, really tight layout for the switch capacitor, or for the SCBA core. And then we flipped it to the board at our matching components. Really tiny. This was done in a 65 nanometer process. The last one was a 90 nanometer process, so this is what I was talking about earlier. We did try multiple generations with successive generations of CMOS. Here we get nice output power characteristic versus input code. Now instead of 64-bit input code, we have 128-bit input code because we have that extra bit in the supply voltage. More importantly, what we wanted to see was that Class G action on the efficiency characteristic. So looking at the efficiency characteristic, at high voltages, the efficiency characteristic rolls off very slowly. We get that second peak in efficiency and then roll off as the result was. Go to switch capacitor power amplifier. Very importantly, is this efficiency characteristic is much better than a similar linear power amplifier. So we see much higher power, much higher average efficiency. Peak efficiency was around 44% for this one, with 24 dB out. Very similar statistics for what we saw before. Looking at linearity, though, if we look at this characteristic, before we definitely saw some kind of second order nonlinearity with respect to input code and output. Here we see we don't really see any nonlinearity, or very little nonlinearity. In fact, we can measure this in terms of its DAC performance. So the integrated nonlinearity is less or minus 1 LSB, and the differential nonlinearity is less than 1/2 LSB. It's very linear, and it's a very good number. Looking at the AM distortion, it's less than 8 degrees. So before we saw it at about 33, 34 degrees. Now we get less than 8 degrees. And this was just from improved layout and also the fact that the process is better. Looking at dynamic measurements, so this is a vector signal analyzer. We have measured EVM of 2.9%. I had this noted without redistortion. This just means that we didn't have to do anything to the input code to distort the input code. Very linear. And an average efficiency of 33%. Now remember earlier I said that the average efficiency of a linear power amplifier, an ideal linear power amplifier with that same envelope would be 5, maybe 10%, somewhere in that range. We get 33%. At least 3 times better, maybe 6 times better, depending on who's designing the amplifier. Pretty good. Now, some of the things that we can do, we have the out-of-band emission problem. So some of the things we can do is instead of running our sampling at 80 megasignals per second, we can increase the sampling rate to 320. And what that does is just pushes the alias terms further out and lets the filter attenuate further, the filtering from the matching number. Just a comparison between some other power amplifiers. And what we really want to look at is the average efficiency. This is what's actually being drawn from your battery as you transmit the signal. We look at this result. We get a peak efficiency of 69%. The average efficiency is only 22%. Here, because of this, the way we shape the efficiency characteristic, our peak efficiency is much lower, but our average efficiency ends up being much higher. Now, what we need to start doing is pushing the average output power up to where it's in the range of these guys. But still, very, very interesting result. So where do we go in the future? These power amplifiers, so most power amplifiers, linearity is limited by the transistor itself. We have to keep the transistor saturated. The transistor has nonlinearities that we have to take care of. Most of the time, the out-of-band spectrum is in a power amplifier is dominated by the transistor. Here, the out-of-band spectrum is dominated by the quantization. So we only have 6 bits of amplitude control. So we have the quantization noise. The quantization noise is white. So we basically have this strong white noise that only gives maybe a second or third order noise shaping due to having 2 or 3 passive components in the output. So one of the things that we need to do is figure out a way to increase the resolution of these power amplifiers, which is very difficult. These are running at 2.4 gigahertz. It's not an easy problem. So this is a future research direction. How do we increase the resolution of the power amplifier and drop that quantization noise down, but also not increase the nonlinearity of the array? Very, very challenging. And then going forward, we also want to make these tunable over frequency. So how do we make them tunable? Well, we need to start making some kind of tunable passive converters. Well, we've already seen a couple of interesting ways to make voltage tolerant switches in CMOS. So if we wanted to make a tunable capacitor, for instance, and this was reported last year, we could take a stack of transistors and selectively either short them out with a voltage tolerant switch or not. And what that would allow us to do is we effectively have a series resonant network. So we could change the size of each of the capacitors in the array, and that would effectively tune the frequency. That would give us an optimal efficiency characteristic, but it would definitely allow it would give us decent efficiency and allow us some frequency tunability. To get good efficiency, we need to add a tunable inductor. So one of the things that I've been looking at is, can we take a slab inductor type shape? So we just take a piece of transmission line and wind it back around on itself, and we can selectively short out segments like this. The reason that we don't typically use transistors to tune inductors is because when we get transistors near inductors, they increase the loss in the inductor for a number of reasons. But mainly having to do with the fact that when the inductor is sitting above a silicon substrate, it has bulk eddy currents that are flowing in that substrate. Those are lossy. When we bring transistors near it, we increase the current, or we increase that the loss in that do that eddy current. Another thing that's kind of interesting is there are new materials. So there was this cool germanium antimonide material that was put in this switch. And this is it's a device. It's programmable between an amorphous semiconductor and a crystalline semiconductor. So they can program it by just sending different current pulses through the material. And that would mean that they could, say, add this series winding to this series winding and increase the inductance that way. So a couple of interesting options. And also we can start playing around with MEMS devices, especially with flip chip packages over low loss substrates. I think I'll just skip through this material, but I'm also looking into some ways to increase energy efficiency on the low power side of things as well. So we're going to make really low power, high efficiency radios so that we can use them for medical implants and sensor networks as well. And so with that, I will just conclude. So I showed you the Capacitor PA and how we can make scaling-friendly digital power amplifiers that are very interesting. And lots of interesting research opportunities. So if you are interested in any of these, stop by my office or send me an email. Any questions? I've sufficiently blown all of your minds.
Have you considered the charge balancing problem of the capacitors? issue with the charge balancing the capacitors when they are in series?
Yeah, so that's where, I mean, that's basically one of the ways that AM-to-PM distortion comes into play. And so we haven't looked into it too much, but just careful layout techniques are always really done to minimize that problem. Who here does circuit research? Good to know. All right. So I guess I don't know if there will be a seminar next week, but